Welcome back. We will continue our discussion of TCP in this lecture. You might hear occasional noise that's coming from firecrackers because our festival of Diwali is coming up. We are going to look at the sliding window algorithm that's used in TCP. And this algorithm is also used to do flow control. So we will see that. TCP is a byte stream oriented protocol, but sending to a small segment causes problems. So we'll see how TCP decides when it's time to send a segment. TCP uses ARG for reliable transmission. However, in the case of TCP, round trip times vary a lot, and therefore TCP uses adaptive timeouts. We will also see how it is done. So by the end of this video, you would know how does TCP sliding window work, how is flow control done in TCP, and how does TCP decide when to transmit and when to retransmit a segment. In an earlier video, we had discussed sliding window algorithm. TCP's variant of the sliding window algorithm serves several purposes. It guarantees reliable delivery of data, which we saw at that time also. And it also ensures that the data is delivered in order. We had discussed these two. If these things are not clear or you don't remember the details, you might want to go and watch that video again. That video is called Reliable Transmissions. In addition to these two, TCP's sliding window also enforces flow control. And last time when we were discussing sliding window, we had a fixed sliding window, right? In the case of TCP, it adapts the size of the sliding window, right? And to do that, it uses advertised window field that is present in the TCP header. So actually the receiver tells the sender how much data it can send that is not acknowledged. Another major difference between the sliding window that we discussed at that time and the TCP's variant is that in the case of TCP, the behavior of application is considered explicitly, as we will discuss in the next slides. This diagram shows the behavior of TCP on the sending side as well as the receiving side. On both sides, TCP maintains a buffer. On the sending side, this buffer contains the data that is not yet acknowledged but sent, and also the data that application has written but that has not been sent yet. On the receiving side, it contains the data that has been delivered in order, but the receiving application has not read the data yet, and also the data that has arrived out of order. And the size of buffers, the maximum size of the buffers, is fixed on both sides. Note that in these diagrams, the sequence numbers increase from left to right. Increases. So all these bytes before the last byte act had been acknowledged, and therefore there is no need to buffer them. And the data that is between the last byte sent and last byte act, that has not been acknowledged at yet, and therefore last byte act would always be less than or equal to last byte sent. They would be equal if all the data that has been sent has also been acknowledged. And then the application writes data as it generates, but some of this may not be sent, maybe because the sending window size is not enough, or maybe just because it just has written some more data that is yet to be sent. And therefore there is another inequality: last byte sent is less than or equal to last byte written. On the receiving side, this is the data that has been received, and it's received in order. So this is the last byte that was received in order, and this much data is missing, it's lost. And then there is some more data that was received, and the receiving application has read the data up to this point. So the last byte read is pointing here. Recall that sequence number increases to the right. So last byte read here by the application is less than next byte expected, because if data is delivered in order, you expect at least one more than the last byte read. Second, next byte expected is less than or equal to last byte received plus 1. There had been some out of order delivery here, so this chunk is missing. But if data was delivered in order, then last byte received would point here, and therefore in that case next byte expected would be equal to last byte received plus 1. But in general, because of this out of order delivery, there would be inequality. And lastly, this max receive buffer is the maximum receive buffer size, and therefore the last byte received cannot be larger than the last byte read here plus the buffer size, right? So that's what this third inequality is saying. Last byte received minus last byte read must be less than or equal to max receive buffer. Let us say that max receive buffer plus last byte read points somewhere here, and because this much data is received in order and acknowledged, and so therefore the receiver can only store this much data that arrives out of order, and therefore it's going to advertise this size as its receiving window size. And other thing to note that here the receiving application plays a crucial role. So if for some reason this application is blocked, it's not able to consume this data, then this buffer is going to fill up at some time, and once it fills up, there is no room to keep any data in this buffer, and therefore the receiver is going to advertise the receiving window size of 0. The receiver informs the sender of the available buffer space through this field in the TCP header, that's advertised window field. And as we discussed before, the value that the receiver is going to send in this field is going to change according to how much buffer space is available. So this advertised window size is equal to the max receive buffer minus the difference between next byte expected minus 1 and last byte read, right? So this is basically, as I explained before, it's suppose max receive buffer plus last byte read comes to that point, then the advertised window is this much. On the sender side, the sender makes sure that the difference between last byte sent and last byte act never exceeds advertised window, right? So this is, in this diagram, it's this much data over there. So on the sender side, the sending window size also changes, like according to the advertised window and how much data is sent but not acknowledged yet, right? And that effective sending window size, right, which is this variable effective window, is the difference between advertised window and the amount of data that has been sent but not yet acknowledged. Here is an example. A receiver allocates 4 kilobyte buffer. The sender sends first segment 2 kilobyte. Suppose it starts at sequence number 0. Then on the receiver side, 2 kilobyte of this buffer is taken, right? So another 2 kilobyte remains, and the bytes that the receiver has received are bytes starting from 0 to 2047, and therefore it's going to put 2048 in acknowledgement, and it's going to advertise a window size of 2048, because that's the amount of buffer space that's available. Next, the sender is going to send a 2 kilobyte segment, and the sequence number is going to be 2048 because it had sent bytes 0 through 2047 before. And now the buffer at the receiver side is full, assuming that the receiver application has not read anything. The next byte expected is now 4096, because another 2048 bytes were received. So up to 4095, all of these bytes have been received. So therefore, next byte expected goes in the AG field. However, in the advertised window, the size is 0 because there is no space on the receiver side. So at this time, the receiver had advertised a window size of 2 kilobytes, right? 2048. Once the sender sends 2 kilobyte of data, right, it cannot send any more data until all of this data is acknowledged. At this time, all of data is acknowledged, but the receiver says the advertised window is now 0, and therefore sender cannot send any data, right, in this space. And so it's kind of interesting because now there is no more acknowledgement that's going to come because the receiver has acknowledged all the data that sender has sent, but there is no buffer space at the receiver, and the sender cannot possibly know until the receiver tells whether application has consumed some of this buffer, and now it can send more data. And so at this time, sender can do two things. Either if there is urgent data, then it can send, and hopefully once the data is received, some more buffer space opens up, and then the sender can resume. And another thing that the sender can do is send what is known as window probe segments. So these are 1 byte segments just sent to figure out whether there is buffer space available, and if that is the case, then the sender can resume further. And so as I explained, the sender sends 1 byte probe segments randomly if the previously advertised window was 0. Another thing to note is that on the sender side, the difference between last byte written and last byte act cannot exceed the sending buffer size, and therefore if the sender tries to write y bytes, and if doing so would exceed the sending buffer size, then TCP would block the sending process, right? And so that's all about the flow control. So to summarize, a fast sending process and a slow receiving process means that this buffer is going to be getting filled as time progresses, and at some time when this buffer is full, the advertised window size becomes 0, And as a result, the sender is not going to send any data to the receiver. And if there is still space on the sending in the sending buffer, then the application can still write data to it. But since the sender side is not sending any data to the receiver, right, so this sending side buffer is also going to fill at some time. And once that happens, the sending process gets blocked until, again, the receiving application consumes some data and the buffer opens up, and then the sending process can resume. Now we are going to look at wraparound of sequence numbers. The sequence number field in TCP header is 32 bits long and the advertised window is 16 bits. And so there are 2 to the power 32 possible sequence numbers as compared to 2 to the power 16 advertised window size. And therefore it easily satisfies the requirement that the sequence number space be at least twice as big as the window size. It's assumed that a segment would survive for 120 seconds. This is referred to as maximum segment lifetime, or MSL. And this is a design parameter, right? It's really not enforced. However, we need to make sure that the sequence number does not wrap around, right, within this time period. And so what it boils down to is how fast the data can be transmitted over the internet, right? So here is a chart which shows the time until wraparound for different bandwidth. For T1 line, it's 6.4 hours, which is quite larger than 120 seconds. Again, for 10 Mbps Ethernet, it's 57 minutes and so on. But you see there are faster networks. These are optical networks where the time until wraparound is actually less than 120 seconds. And in these fast networks, TCP deals with this problem by also sending a timestamp. And so the 32-bit timestamp is prefixed to the 32-bit sequence number. And so even though the sequence number wraps around, the timestamp keeps increasing, and therefore basically the wraparound does not confuse the receiver. Next, we are going to discuss the issue of keeping the pipe full. That this 16-bit advertised window field must be large enough to allow the sender to keep the pipe full. Of course, the receiver is free to not open the window as large as the maximum that advertised window allows, which is 64 kilobytes, if there is not enough buffer space. However, if there is enough buffer space, then the sender should be able to send full delay bandwidth product worth of data. And to see whether the 16-bit advertised window allows, we'll just focus on one example. So we are assuming that in this example the round trip time is 100 milliseconds. And so for T1, the delay bandwidth product comes out to be 18 kilobytes, right, which is less than 64 kilobytes that the 16-bit advertised window field allows. However, for all other speeds, these numbers are larger than 64 kilobytes. So clearly the 16-bit advertised window is not sufficient for these networks. In the case of high speed networks, there is a scaling factor that is used in TCP. And so basically what it means is that whatever is in the advertised window, we basically multiply with this scaling factor. So it could be, for example, chunk of 16 bytes and so on. Next, we are going to discuss how does TCP decide it's time to transmit the next segment. Remember, we talked last time, TCP supports a byte stream abstraction. That means application programs write bytes into streams. Now it is up to the TCP to decide it has enough bytes to send a segment. TCP maintains a variable called maximum segment size or MSS, and it sends a segment as soon as it has collected enough bytes from the sending process. So as soon as the number of bytes exceeds or it's equal to MSS, it will send a segment. And this MSS is usually set to the size of the largest segment that TCP can send without causing fragmentation. And so this is equal to MTU of directly connected network minus the size of TCP and IP headers. If the TCP sender sends the segments aggressively without really filling a segment up to MSS bytes, what happens is that there is a phenomena called silly window syndrome. Right? And so what happens is that these smaller than MSS size segments sort of persists over time. Right? And to understand this silly window syndrome, think of TCP stream as a conveyor belt. With some of the containers are full, right? So they contain MSS worth of data, and some are not full, so they contain less than MSS worth of data. And on the other side, from the receiver, empty containers containers return, right? And they basically are the acts. And so here is an illustration of that. So from the sender, MSS worth of segments go, and receiver acknowledges MSS worth of segments. And so if the sender is aggressively sending and if the application is generating enough data, there's no problem. However, if the application is not generating enough data, right, then if the sender is sending aggressively, what may happen is that it sends an MSS worth of segment, then some other segment does not contain that much data, and what comes back is these acknowledgements. So then the sender gets this MSS worth of window open, so it will send an MSS worth of segment, and then it gets an acknowledgement for a segment that was, let's say, half the MSS size, and then it will send this half this MSS size segment. This will just continue forever. And so these segments that are not full MSS size sort of persist over time, and that's referred to as silly window syndrome. So this is what I just explained to you. So if the sender aggressively fills an empty container as soon as it arrives, then any small container introduced into the system remains in the system indefinitely, because it is immediately filled and it's also emptied at each end, and never it's coalesced with adjacent containers to create larger containers. And so if there is data to send, right, but the window is open less than MSS, then what should the sender do? Right? The problem is it may want to wait for some time before sending, but how long should it wait? Because it does not know when the application is going to write enough bytes into the stream so that it can send MSS worth of data. And note that if it waits too long, then it will hurt interactive applications, and if it does not wait too long, then this silly window syndrome will persist. So the solution of this problem is to introduce a timer, and sender waits until the timer fires, and if if it accumulates enough data, then it sends immediately, but if it does not, then it waits for the timer to fire. And we can use some clock based timer, but then it will not be appropriate for all sorts of applications, right? So there has to be some applications that may require less, some require more. So what do we do? So there is an algorithm called Nagels algorithm, and this is this algorithm basically it's a self clocking solution to this silly window syndrome problem. So the key idea behind Nagel's algorithm is that as long as TCP has any data in flight, the sender will eventually receive an ACK, and this ACK is treated like a timer. Right? So whenever an ACK is received, a decision is made whether a sender is going to send more data or not. Here is Nagels' algorithm. Right? So essentially what it says is that if the available data and the window are both larger than or equal to maximum segment size, then send a full segment. Right? Otherwise, if there is unacknowledged data in flight, then buffer the new data until an ACK arrives, and then go back and make this decision again. Right? So it does not again mean that when an ACK arrives, you send whatever is there immediately. You just do this process again. And if none of this is true, so if the available data is less than the maximum segment size, and whatever the window is, whether it allows if the window allows sending the data even though the data may be less than maximum segment size, and if there is no unacknowledged data in flight, then send the new data now. In the case of interactive applications like telnet, some of these segments will contain just 1 byte, or some other segments would contain more data, right? And the other thing is that in the case of applications where interactivity is more important, then one can turn off the Nagel algorithm by setting this TCP no delay option. TCP provides guaranteed delivery using ARC that we studied quite some time ago. And ARC involves setting timeouts and retransmissions if acknowledgements don't come before the timeouts. The problem with TCP is that the two endpoints could be very far apart, could be quite near, and therefore there is quite a variation in terms of round trip time. So setting one fixed round trip time is not going to work. And even more so between the same endpoint pairs, right? The round trip time may vary over time, because of maybe congestion, maybe loads differ from router to router, maybe it takes different paths and so on. And therefore timeouts need to be set dynamically in TCP. The original TCP implementation used a simple algorithm to compute timeouts. So what happened is that when a sender would send a segment, it would record the time that it sent the segment. And then when it receives an ACK for that segment, it would subtract the sent time from the received time to calculate the round trip time for that segment. And then it keeps weighted average, right, of these round trip times. And this is a fairly general sort of procedure you will see at several places. This is called smoothing. So this new RTT estimate is computed as alpha times the previous estimate plus 1 minus alpha times this sample RTT that represents the round trip time of the recent segment. And in this algorithm, alpha was kept between 0.8 and 0.9. And then for the segment that the sender is going to send, it's going to set the timeout as twice this estimated round trip time. So suppose alpha is 0.8 and the estimated RTT previously was 100 millisecond, and the most recent sample RTT is 120 millisecond, and then the new estimated RTT is going to be 0.8 times 100 plus 1 minus 0.8, which is 0.2 times 120, and that's 80 plus 24, which is 104 milliseconds. So as you can see that this fluctuation in round trip time was 20 milliseconds, but because of this smoothing, it went down to 4 milliseconds. Well, a problem with this algorithm is that the acknowledgements acknowledge data and not a retransmission. So when a segment is retransmitted and then an ACK comes, it is impossible for the sender to decide whether the ACK is associated with the original transmission or the retransmission. So here is a diagram that shows that. This original transmission followed by retransmission and ACK. So if the sender associates this ACK with the original transmission, then this actually is overestimation of round trip time, because round trip time is only this much. On the other hand, in this case, there is original transmission followed by an ACK, but the ACK was delayed and therefore there was retransmission. And so if the sender associates this duration as the round trip time, then this actually underestimates, because the actual round trip time is this much. A solution to this problem was proposed by Karn and Partridge in 1987, and their algorithm has two parts. So first, we do not sample round trip time when we are retransmitting. So in this case, when we are retransmitting, we do not calculate the sample round trip time in this calculation, right? So it's basically we skip this calculation for all the retransmissions. And the second part says that we double the timeout after each retransmission, right? So again, instead of calculating the round trip time and estimated round trip time and then timeout from that, twice the estimated round trip time, we simply double the timeout after each retransmission. Something that should remind you of our discussion of Ethernet. This is essentially exponential backoff that we saw at that time. A problem with the timeout computations and also Karn and Partridge algorithm is that it does not take the variance of sample round trip time into consideration. And if the sample round trip time does not vary much, then the estimated round trip time can be trusted. Remember, in our calculations, we calculate the estimated round trip time and then we set the timeout to be twice the estimated round trip time. So if there is not much variation in estimated round trip time, the timeout could be equal to estimated round trip time, right? So that's the point. On the other hand, if there is large variance in the samples, then the timeout should not be really tightly coupled with the estimated round trip time, right? And so this was recognized and fixed by these two people, Jacobson and Carls, just 1 year after Karn and Partridge algorithm. It was 1988. In Jacobson-Carls algorithm, we keep a running average of two quantities, estimated round trip time and deviation. And for computing estimated round trip time, we use this equation. So we take the previous estimated round trip time and then we add to it delta times difference, where difference is sample round trip time minus estimated round trip time. And we have seen such a thing before, right? So previously we had estimated round trip time is alpha times estimated round trip time, right? This is the previous one, and then 1 minus alpha times the sample round trip time. So if you compare that equation with this one, delta is basically 1 minus alpha, because if we expand this, you have estimated round trip time is equal to estimated round trip time plus delta times difference, which is sample round trip time, right? um, Minus, again let me just expand it here itself, delta times estimated round trip time, right, which is 1 minus delta times estimated round trip time plus delta times sample RTT. And so what is delta here was 1 minus alpha over there. And so this is again basically the smoothing. And the next quantity whose running average is kept is deviation. Again, this is a smoothing as you would recognize. In case of deviation, the estimated deviation is equal to the previous deviation, right, plus delta times again mod of the difference minus deviation, because realize that the sample round trip time may be larger or smaller than estimated round trip time, and accordingly the difference would be positive or negative. However, we are interested in variance, and therefore we take the absolute value of the difference and then subtract from the previous deviation, right? Again, this is also smoothing. And finally we compute the timeout as again some parameter mu times estimated round trip time plus another parameter phi times the deviation. And for these parameters, delta is between 0 and 1, and typically mu is set to 1 and phi is set to 4. So when the variance is small, timeout is close to estimated round trip time, because as I said, mu is set to 1, timeout is equal to estimated round trip time, right? If the deviation is small, this term basically does not contribute much to the timeout. On the other hand, if the deviation is large, then this term is going to dominate. The efficiency of TCP in the case of high performance networks is managed using TCP extensions. And so remember that there is a header length field in case of TCP header, right? So because of this, there is possibility to add options after the standard header fields, and they are called TCP extensions. And so to put an option, there is one byte option type, right? So there are therefore there are 256 possibilities for options. These options are managed and a list of these are maintained by IANA, and IANA defines 255 out of these 256 possibilities. One of the options is 32-bit timestamp. So when the sender sends a segment, it will set this option and then put a 32-bit timestamp. Right? This timestamp, works for two, goals. First is that it helps in round trip time calculation, because the receiver is simply going to echo this round trip, this timestamp that was sent by the sender. And so the sender would simply subtract its from its current time, this timestamp, and can calculate the round trip time for this particular segment. And therefore this issue of retransmission that we were discussing, it solves that problem. And the second, as I mentioned, we use this timestamp and sequence number together, right, as basically a sequence number to fix this wraparound problem in the case of fast networks. And again, we discussed the use of a scaling factor, right, to cope with filling the pipe when we have fast links. And so the scaling factor that we use in advertised window is also sent as an option. And there is also a SAC option, or SAC stands for selective acknowledgement option. When this option is used, then the receiver sends the acknowledgements in a normal way that it does, but then it also acknowledges the data that it has received out of order, right, as the selective acknowledgements. This selective acknowledgement helps the sender because sender now needs to only retransmit the missing bytes. So suppose the bytes 100 to 150 are received in order and also acknowledged, and if the SAC option is used, the receiver can also acknowledge these out of order bytes, so bytes, let's say, from 200 to 250. And therefore, when the sender resends, then it needs to only resend these bytes from 151 up to byte 199. Okay, to summarize, we saw that in the case of TCP, the sliding window algorithm also incorporates the data consumption and generation of the application process. This is something that is new as compared to the sliding window discussion that we had earlier. And we also saw that the TCP sliding window implements flow control using this advertised window size field, right, that it sends along with the acknowledgement. And this advertised window size is used to throttle the sender. It's according to whatever buffer space remains, the sender could even be blocked from sending data. And we also saw that there is something called silly window syndrome that happens when the sender sends the data aggressively. If there is not enough data and sender just immediately sends, then it's possible that that a small segment would persist, right? And we use Nagels algorithm to fix that problem. And this algorithm basically says that if you have enough data more than or equal to 1 MSS, then the data should be sent right away. Otherwise, if there is data in flight, then you need to buffer. And lastly, we saw that TCP sets these timeouts for retransmissions adaptively. And we saw original TCP algorithm, and we saw Korn and Partridge algorithm. Lastly, we saw Jacobson and Carls algorithm, and this last one uses a smoothing. So the current estimate is it's a weighted average of the previous estimate and the current sample, and it also factors in round trip time variations. That's all in this video. Bye for now.